Hi guys, welcome to another episode of MrLopezClasses.com. This is the chapter number 4. We are going to talk about the combustion chamber in diesel engines. The combustion chamber. This is the area where the majority of the problems start in the combustion chamber. And we are going to check today in this video what happens if in the combustion chamber we have excess of fuel, or what happens if we have excess of air, what happens if we have intrusion of coolant, what happens if we have intrusion of salt water, what happens if we have intrusion of oil. And those are the problems that we are going to solve it in the next episode of this chapter. Okay, welcome to the chapter number 4, the combustion chamber. Okay, remember the combustion chamber is the area created for the head and the piston. Remember that the majority of the diesel engines, the head is flat. The head is flat with the valves on the head. However, the pocket for the combustion chamber is created in between the head and the piston, because the pocket is located on the piston. The piston that you have on the screen right now, in that pocket is created basically the volume of the combustion chamber. That specific pocket, if you remember, I explained before, have that design in order to concentrate the forces through the center of the connecting rod. This is a special design, good in order to concentrate forces and avoid noise. We are going to verify the different types of combustion chamber. What is the combustion chamber? It's the space at the head end of an internal combustion engine cylinder where most of the combustion takes place. Yeah, it's the area in between the head of the piston and the valve head where the combustion is produced. In diesel engines, the combustion is initiated when the fuel enters in the combustion chamber at the end of the compression stroke. It's used at the end. Some degrees before, is around in between 4 and 6 degrees before top depth center, the injector open and inject the fuel. How is possible that the injector open at that specific moment? Yeah, this is the timing, and we are going to talk later how is the procedure to put the engine on time in order to be 100% sure that the injectors open exactly in the moment required for the manufacturer. Each manufacturer have special recommendations in relation with the moment of the injection. If it's 6 degrees or 8 degrees or 10 degrees or 4 degrees before top the center. Normally it's before, not after. I'm going to explain later why it's before and not after. Alright, in diesel engines we have basically two types of combustion chambers, and the type of combustion chamber depends where is located the injector. In other words, the combustion chamber is direct fuel injection. If the injector, like in this particular case, is located inside in the middle of the combustion chamber. In this particular case, the injector inject the fuel here, inject the fuel over there, and concentrate the force in the center. In the second one, in indirect injection, the injector inject the fuel not directly into the combustion chamber. The injector inject the fuel in a pre-chamber, in this pre-combustion area. In that pre-combustion area, normally is located this element, the preheater or glove plug. The function of the glove plug is preheat the pocket of the piston in the pocket of the combustion where the combustion takes place. The injectors are a little different. The nozzle of the injectors is a little different in comparison with the injectors of direct fuel injection. The injector with direct fuel injection use a nozzle with holes, and this one use the pintle nozzle that we are going to study later. The majority of the new diesel engines, they use this combustion chamber. Alright, we are going to check the most common shapes of combustion chambers. This is one of the most famous head. This is like a triangle. It's like a triangle located here. This is the wedge shape. It's used in gasoline engines. The majority of the Merc Cruiser inboard engines, they have that shape on the head. If you see the picture that you have on the screen right now, this small pocket is used to protect the face of the valve. Because if for some reasons in gasoline engines, you remember the timing chain is broken or the timing belt is broken, what happened in that case? The valve stay open, and when the piston is going up, touch the valve, destroy the valve, with catastrophic consequence, like the picture that you have on the screen right now. This is the typical situation where the timing chain is broken or the timing belt is broken, and the piston hit the valve and destroy the engine. Because when you have that situation, the engine is completely deteriorated. Alright, this is very common in gasoline engines. It's no longer used in diesel engines. In diesel engine, the majority of the heads are flat heads, like this, with the valves directly in front of the piston, like this. This is the typical head used in diesel engines. This is the flat head with the valves on the head. For example, suppose that this is the intake valve. The intake valve is located here, and here is located the rocker arm. And let me complete the picture. This is the picture for the rocker arm, and right now this is the push rods. This is the push rods, and here you have the lifters, and here you have the valve of the camshaft. This is the typical situation and this one probably is connected with the intake manifold. This is the intake manifold. The intake manifold is connected here, and here probably is connected the throttle body. The throttle body is located here, and the air enter over there. This is the typical shape of the head in a diesel engine, flat head. And this is the injector. The injector is connected with the fuel injection pump, and the fuel injection pump engage with the gear of the crankshaft and the gear of the camshaft. This is the flat head used in a diesel engine. Alright, right now we are going to start about the fuel-air mixture and what happened with the mixture in between air and fuel. This is the critical part of any type of engine. Remember, in previous episodes, I explained that when you compress pure air, depending how is the seal in the combustion chamber, you can reach temperatures normally around 1000 degrees Fahrenheit or maximum 1400 degrees Fahrenheit. It's a high temperature in the combustion chamber, especially in diesel engines. However, when the air is mixed with fuel and you compress that mixture, you don't reach those temperatures. You reach lower temperature. This is the case of the gasoline engines. In our particular case, in diesel engines, the temperature on the head is around 1000 degrees Fahrenheit, maximum 1400 degrees Fahrenheit. In order to avoid that the air coming from the turbo entering into the combustion chamber with excessive temperature, the majority of the diesel engines, they have an intercooler or aftercooler. What is the function of the aftercooler? The function of the aftercooler is reduce the temperature of the air before the air enter with high pressure into the combustion chamber. What happens if the air enter with excessive temperature? For example, 1500 degrees Fahrenheit. If the air enter at around 1500 degrees Fahrenheit, when the fuel, the liquid fuel, is injected in the combustion chamber, immediately the fuel enter, the fuel become vapor, and during the explosion, that vapor is not good because eroded the face of the valves and destroyed the valves. The name of that phenomenon is vapor lock. In order to avoid vapor lock, the temperature of the air before the air enter in the combustion chamber is reduced. In the intercooler or aftercooler. The aftercooler is a heat exchanger. The salt water enter in one side, goes into the other one, like the picture that you have on the screen, and the air pass from the input in this side, and the output goes directly into the intake manifold. All right. This is the element used to reduce the temperature of the air before the air enter in the combustion chamber, and in order to avoid vapor lock. Vapor lock can be produced also if the fuel enter in the combustion chamber with high temperature. For that reason, the majority of the diesel engines, they use a cooler for fuel. Oh yeah, remember I explained there are around 6 heat exchangers in a typical diesel engine. One heat exchanger for the engine, for the motor oil, other heat exchangers for the coolant, other heat exchanger for the air, the intercooler, other heat exchanger for the transmission oil, other heat exchanger for the fuel, and other heat exchanger for the hydraulic liquid of the power steering system. Yeah, there are around 6 heat exchangers in a typical diesel engine. All of those heat exchangers use the salt water in order to reduce the temperature of each fluid corresponding. All right. In this particular case, in order to avoid vapor lock, there are 2 heat exchangers involved in that situation. One heat exchanger to reduce the temperature of the air, the intercooler, and other heat exchanger in order to reduce the temperature of the fuel. Is the fuel cooler. Other important thing, why the temperature of the fuel is too high if the fuel is coming from the fuel tank. Remember that the fuel in diesel engines, the fuel entering in the fuel injection pump, only 20% of that fuel is used to enter in the combustion chamber and produce power. The rest, 80% of the fuel, return to the tank. All the injectors, they have one input in one of the sides and one return on top. Okay, the fuel entering, only 20% enter in the combustion chamber, and 80% of the fuel with high temperature return into the tank. What happened with the fuel tank in your boat after 1 hour of operation? Probably the fuel tank is too hot. For that reason, the fuel return into the engine and pass through the fuel cooler before the fuel enter again into the fuel injection pump. All right, so that's very important. The combustion process in a diesel engine is initiated by spontaneous ignition of fuel when the fuel is injected at high pressure into the air at high temperature. Normally the temperature of the air is in between 1000 and 1400 degrees Fahrenheit. In a diesel engine, the fuel is injected into the combustion chamber at the end of the compression stroke. right? Normally, I explained to yours, is in between 8 and 4 degrees before the piston reach the top, the center. The fuel enter in the combustion chamber because the injector open, mechanical injector or electronic injector. All right. Okay, now we are going to start to talk about the different type of mixtures between air and fuel. The liquid fuel is usually, don't forget, the fuel entering in the combustion chamber is always liquid. It's not vapor, because if it's vapor, produce vapor lock. The liquid fuel is usually injected at high velocity as one or more jets through the small orifice or nozzles. We are going to study later the nozzle of the fuel injector. It is atomized in small drops and penetrate into the combustion chamber. Yeah, this is the situation. All right. The ideal stoichiometric air-fuel ratio for the majority of the gasoline engines is in between 14.7 parts of air per 1 part of fuel, or 15 parts of air and 1 part of fuel. What is the meaning of that? The appropriated ratio air and fuel for gasoline engines is 15 parts of air per 1 part of fuel. 15 air and 1 fuel. If that proportion is 15 to 1, the gasoline engine is running in good conditions, in good operational conditions, good temperature, good pressure, and good performance in gasoline. In diesel, that stoichiometric ratio have too much variations, and the less stoichiometric ratio is around 18 to 1 and goes until 160 to 1, more than 70. It's 70 to 1, no, it's going until 160 to 1 when the engine is turbocharged or supercharged. In other words, works in between 18 and 160. 18 is for naturally aspirated. Remember, the naturally aspirated is only with the atmospheric pressure. Okay, the stoichiometric ratio in diesel engines have a big range of compressions, of pressures. Yeah, depend if the engine is naturally aspirated and if the engine is turbocharged or supercharged. And now we are going to check what happened in each situation. Fuel-air ratio. In this slide, we can check that the air-fuel ratio at the peak torque is usually around 25 to 1 for naturally aspirated engines, and the maximum is a little bigger than 160 to 1 for supercharged engines. Oh, it's a lot, no? What is the meaning of that? I can introduce, if the engine is supercharged, I can introduce 160 portions of air per 1 portion of fuel. With 1 portion of fuel, I can burn it more air in a diesel engine. Yes, for that reason the diesel engine is highly efficient in comparison with the gasoline. The typical gasoline engines with the same part of fuel, with 1 part of fuel, only burns around 15 parts of air. And the diesel engine, supercharged, burns with the same part of fuel 160 parts of air. That's the main comparison. Yeah, this is a big difference. All right, in a typical diesel engine, the air-fuel ratio 60 to 1. This is the air-fuel ratio at peak torque. You remember what is the peak torque normally for diesel engines? Is in between 1400 RPMs and 1800 RPMs. In that range, in the majority of diesel engines is produced the peak torque, the maximum torque possible. In that area, in between 1400 RPMs and 1800 RPMs, the recommended stoichiometric ratio for turbocharger or supercharger engines is 60:1. No? And of course, if in supercharged engines, supercharged engines, the stoichiometric ratio, the air-fuel ratio, is around 160:1 when the engine is in idle. When the engine is in idle, the stoichiometric ratio increases. What is the meaning of that? In idle, the engine burns more air than at the peak torque. But you need to operate your engine at the peak torque because this is the operational area where you need to run your engine. Okay, in general terms, in diesel engines, charged, turbo or supercharged, the stoichiometric recommended at peak torque is 60:1. Alright, my friends. Remember, in a diesel engine, only the air is compressed, not the fuel. It's only the air. And the fuel enters in the combustion chamber because the injection pump sends the fuel with high pressure and open the injector is at that specific pressure. For that reason, the pressure of the fuel is very important in order to enter in the combustion chamber with the appropriate pressure. Remember, what happens if in the combustion chamber, suppose you have 1200 degrees Fahrenheit and you have 1000 psi of pressure in the combustion chamber. The pressure of the fuel coming from the injector should be superior to 1000 psi. If not, the fuel never penetrates that combustion chamber. All right? The pressure of the fuel is critical, and the pressure of the fuel injection pump should be calibrated periodically. I'm going to explain later in the interval of services where should be calibrated the fuel injection pump and where should be calibrated the injectors. Right now, we are going to calculate the volumetric efficiency of an engine, and we are going to calculate the compression ratio of an engine. Before of that, we are going to try to keep in mind that the air-fuel ratio recommended for diesel engines is around 60:1 in the range of the peak torque, and the maximum stoichiometric ratio when the engine is in idle should be around 160:1 for in idle for engines supercharged. Don't forget that important information. In gasoline engines, remember, the proportion is 15:1, 14.7:1. This is a big difference in between gas and diesel engines. Right now we are going to start to explain what is the meaning of volumetric efficiency. In order to understand that phenomenon, we are going to calculate the piston displacement and the engine displacement. What is the meaning of piston displacement? Piston displacement is the amount of air that the piston can suction when the piston goes down and the intake valves are open. What is the maximum amount of air that the cylinder can fill when the piston is going down and the intake valve is open? You hear that your engine is 4 liters or 5 liters? Yeah, it's because the volume of this cylinder, the volume of air of this cylinder, plus this, and this is 4 liters. This is the explanation for that number. My engine is 5.8. How many cylinders? 8 cylinders. It's because cylinder 1 plus 2 plus 8 in total is 5.8 liters. Or 350 cubic inches. Yeah, we are going to explain what is the difference between one and the other one, or what is the meaning of that. Okay, this is the nomenclature, and I want that you pay attention to this explanation. When the piston is moving from the top dead center into the bottom dead center, that movement, the name of that movement is the stroke. The stroke is the movement in between the top dead center and the bottom dead center. This is the stroke. You remember that there are engines with 4 strokes, 4 movements, or 2 strokes, 2 movements. Yeah. All right. The stroke is the movement complete between bottom and top. All right. And the area located in this section, this is the volume of the combustion chamber. This is the volume of the combustion chamber. This is that small pocket, that small rectangle. Is the area located when the piston is in top dead center and the head. That small area is the volume of the combustion chamber. All right. Okay. And other important recommendation for this example, we are going to suppose that the engine is spinning clockwise, is rotating clockwise. Top dead center is on the high, and bottom dead center is in the bottom. All right. The diameter, the name for the diameter of the cylinder is the bore. Bore is equal to diameter of the cylinder. Diameter of the cylinder. All right. Okay, now we are going to calculate, the first operation is to calculate the piston displacement. How much is the amount of air that the piston suction in one complete movement if the intake valve is open? How many air can introduce the piston when the piston is going down? We are going to calculate the piston displacement. In order to understand easily piston displacement, we are going to refresh our concept of geometry. And we are going to refresh how to calculate the value of a cylinder. The value of a cylinder is basically the base area times the height. Is the base area times the height. Okay, in our particular case, the base area is the area of the piston head. And the height is the stroke. How much is the area of the head of the piston? Okay, the area of the head of the piston is pi times the radius square and times the height. The height is the stroke. This is piston displacement. This is piston displacement. All right. I want to put the area of the head of the piston in terms of the diameter, not in terms of the radius. Okay, I am going to replace the radius for the diameter divided by 2. Okay, this is equal to pi times the diameter divided by 2 square times the stroke. This is the piston displacement. What is the other name for the diameter of the cylinder? Is the bore. Okay, I am going to replace pi times the bore square divided by 4 times the stroke, and this is piston displacement. Very, very simple. All right, it's pi times bore square divided by 4 and times the stroke. This is a simple formula, and this is the value of air in one cylinder when the piston is going down. And what is the engine displacement? Engine displacement is the value of air in one cylinder times the number of cylinders. For example, I have a V8 engine. The engine displacement is equal to the piston displacement times A. Okay, in this particular case is pi times the bore square divided by 4 times the stroke and times A, because it's a V8 engine. This is the engine displacement. I have an example. You have this example in your book. We are going to calculate the engine displacement for the typical 427 V8 Chevy. And we have some measurements. We know the bore. The bore is 4.312 inches, and we know the stroke is 3.65, and we are going to calculate the engine displacement. All right, in this particular case, we are going to calculate the engine displacement for a V8 engine. We know the bore, we know the stroke, and the formula says that the engine displacement is equal to pi times the bore square divided by 4 times the stroke and times the number of cylinders. In this example, the engine displacement is 426.3, and you can approximate to 427, and this is the famous 427 cubic inches. Yeah, this is a very common procedure to calculate the engine displacement. If you know the bore, if you know the stroke, and you want to know the amount of air in total that the engine can suction when the pistons are going down. With this formula, you can calculate, for example, the bore if you know the engine displacement and the stroke, or you can calculate the stroke if you know the engine displacement and the bore. This is very important, my friends, this formula, if you want to improve the performance of the engine. If you want to reduce the volume of the combustion chamber, right now we are going to talk about that. If you want to install a turbocharger in your engine that right now originally is naturally aspirated. In the chapter dedicated to the turbos, I am going to explain the procedure step by step to calculate the turbo appropriated for that particular engine. This is a wonderful video that I hope that you enjoy. How to calculate, how to size the turbo appropriated for my engine. Alright? Okay. For that reason, this formula is critical, it's very important. We are going to solve it an example. Suppose that we have the famous Chevy 350. Okay, is the engine displacement is 350 cubic inches, and suppose that the bore for that engine is for example 4.2 inches, and the question is how much is the stroke, how much is the distance that the piston travel from the bottom to the top. Okay, we are going to use the formula engine displacement is equal to pi times the bore square divided by 4 times the stroke and times the number of cylinders. Okay, in this particular case the engine displacement is 350 and is equal to pi 3.1416 times the bore is 4.2 square divided by 4 and times the stroke, this is the question, and times the number of cylinders, 8 cylinders. Okay, in this particular case the stroke is equal to 350 times 4 and divided by pi 3.1416 times 4.2 square and times A. This is the value of the stroke in inches. Simple. This is the formula to calculate the stroke. Yeah, we can use this formula to calculate the bore, to calculate the stroke, or to calculate the engine displacement. We are going to talk about the compression ratio. What is the meaning of the compression ratio? When you buy a car, you see on the catalog, in the catalog they say, oh, the compression ratio of this car is 10:1, but the other model is 11:1. Or, what is the meaning of that? And what happens if the compression ratio is higher? My car is better? Or what happens if the compression ratio is lower? I have less efficient or more efficient? What is the meaning of that? Okay, we are going to try to understand what is the meaning of compression ratio. But it's very simple. You remember when the piston is in top dead center? You remember that small value? What is the name of that value? It's the volume of the combustion chamber. Okay, and you remember what happened when the piston is in the bottom dead center? Yeah, this is the total value of the cylinder, no? And this is the value only of the combustion chamber. Compression ratio is, let me check if I can introduce that small value of the combustion chamber in the total 1, 2, 3, 4, 5, 6, 7, 8. The compression ratio of this engine is 8 to 1. That's clear? Is the value of the combustion chamber, how many times you can divide the total into the volume of the combustion chamber. This is the definition of compression ratio. In a piston engine, is the ratio between the value of the cylinder and combustion chamber when the piston is in the bottom and the value of the combustion chamber. It's very, very simple. For that reason, the simple formula for compression ratio is this. The simple formula for compression ratio is this. Is the value of the piston displacement plus combustion chamber divided by the value of the combustion chamber. Simple. Yeah? The piston displacement plus combustion chamber divided by the combustion chamber. This is the compression ratio. Simple. In diesel engines, calculate the value of the combustion chamber is too simple. Because if you have the piston that you have on the screen right now, you can fill that pocket with water, and you can calculate in a special jar with the division in ounces or milliliters how much is the value of the combustion chamber. And you know the value of the combustion chamber, and additionally you know the piston displacement when the piston goes down. Okay, and now you can calculate how many times you can introduce that volume in the total length, and this is compression ratio. It's clear, my friends? We are going to refresh quickly. Compression ratio is the volume of the piston displacement plus the volume of the combustion chamber divided by the volume of the combustion chamber. What do you think in terms of performance is better? An engine with higher compression ratio or lower compression ratio? In this one, we are going to talk about this one. Yes, of course. An engine with more compression ratio, what happened when the piston is at the end of the compression stroke? What happened? The air reached the maximum pressure and temperature. This is ideal. When you introduce the fuel ignites immediately. Yeah? What happened in a diesel engine when the compression ratio is too low and the piston is on the top, the center? Probably the pressure and temperature is not the adequate pressure and temperature in order to ignite properly the fuel. High compression ratio is better. No? With high compression ratio, you can produce better explosions. In gasoline, depending on the compression ratio, you select the fuel appropriate. You select the octane of the gasoline appropriate. In diesel, it's a little different. In diesel, we don't talk about octane, we talk about cetane, and we are going to talk later in the chapter dedicated to fuels what is the cetane appropriated for diesel engines. But in general, the cetane of the diesel that you find in the gas station have the same value for all the different type of diesel. It's clear? This is compression ratio. The compression ratio is another critical and important measurement, because depending of the compression ratio, the performance of my engine is better. And that information, the value of the compression ratio, will be very important in later chapter when we calculate the turbo. In the moment that we do the calculations in order to know how much CFNs and how much boost pressures are recommended for the turbo for that engine, we need that calculation. We need the compression ratio and we need the volumetric efficiency of the engine displacement. We need the engine displacement and the compression ratio. This is the simple term about compression ratio, engine displacement, and piston displacement. Other concept that we are going to use later is volumetric efficiency. Right now, with this formula, with the formula of the engine displacement, we calculate in theory how much is the amount of air that my engine suction when the pistons are going down. 5 liters or 4.7, according with the formula. but this is the ideal. How much is the real amount of air enter in the combustion chamber in this moment when the piston are going down with the intake valves open? Oh, it's not 4 liters, it's 3.83. Let me check that. If you have this slide, we are going to talk about volumetric efficiency. Volumetric efficiency. What is the meaning of volumetric efficiency? Is the actual volume of air divided by the theoretical volume of air. In other words, the volumetric efficiency is the actual, the real engine displacement divided by the theoretical engine displacement. The theoretical engine displacement of this engine is 5 liters. But really, today, only I have 4.7. The volumetric efficiency is 4.7 divided by 5 times 100. This is the volumetric efficiency. Finito. This is volumetric efficiency. Yeah. Why the actual amount of air that the piston suction when the piston goes down is a little less than the theoretical? Because you have leaks, because your engine is 200,000 miles, because the valves don't close properly, because you have a small leak in between the head and the block on the head gasket, because there are too much leaks, because there are dissipation of heat. In general, the real value is not exactly the same like the theoretical. Normally it's less. Yeah, for that reason the efficiency is impossible, 100% of efficiency. Probably in the moment that the engine is new at the sea level, probably is 100. But with a couple of miles running, the efficiency goes down. This is volumetric efficiency, and we are going to study that concept later. Once again, in the moment that we study the turbochargers and the superchargers, we are going to talk in detail about volumetric efficiency. But we are going to use those concepts that we learned today: piston displacement, engine displacement, compression ratio, and volumetric efficiency.